Let's go. Okay, yeah. Okay. All right. Okay, so if you have any feedback on David's lecturing, okay, I'd appreciate you you don't have to give it in public, but things to help him, or compliments or criticism, because I think one of the things he might like to do in the future is be a professor too. So if you gave him some feedback, I could give to him, right? Good. So yeah, I got some good positive comments about it. So that was good to hear. So appreciate that. Okay, let's see. Project. Okay, so project is ongoing. Now let me warn you: don't wait till Tuesday next week to start this thing, right? It's going to be a big shock if you do, right? So point is, start early. I'd say you should be starting on the project now. Another important announcement is this project I intended for you to have partners, okay? So everybody can have a partner on this project, okay? And I know it says do it alone, but when you read do it alone, think partner. It was a little, what I mean, it was a little miscommunication between myself and I was gone last week, right, and the TAs. I wanted this project for you to have a partner. The future ones we probably won't, okay, right? Right. So you don't have to have a partner if you don't want to, right? Yeah.
So can we change the report to 2%?
Yes. So 2 persons, 1 report. So basically you choose a partner, work together, and you turn in 1 report. You both get exactly the same grade. Okay? So we may do it. We will decide whether we'll do the next project as well as with partners, but probably the end one will not be for sure. Okay, right. So the purpose of this project, it's only 5%. It's counted fairly lightly. The purpose of this one is because there's going to be a lot of startup issues, just getting used to the old idea of what a design is, and that's you can share the pain. That's kind of what I want to do. So that's why I want to do it this time. How do you do these projects? So I had a couple of questions on that in the in my office hours today. The way to start these projects is ideally, if you had lots of experience, which is probably not your situation at this point in time, right? You'd look and sort of see what is the really tough specs that I need to meet. Then you would start with a topology that kind of was addressing those very tough specifications. Okay. Well, you don't have a lot of experience, so okay, what do you do then? Okay, well, I would say what you do is you start with the simplest circuit you possibly can that seems to fit what's going on, right? And you need a differential input. You got to have some ability to work over a common mode range of like I don't know, half a volt or 6/10 of a volt. So that probably means you need a differential pair-like circuit in the front there, because that's the only way you can get that kind of common mode range. Okay, if you try to use some single-ended circuit, it's just not going to have that kind of range. You also have a fairly large output swing where the signal has to be valid over. It's going to be tough, you'll find pretty quickly, to have one stage that does both of those things simultaneously. Okay, but try it. I mean, try with a simple differential pair and see if you can make it work, because that's easier to work with if you only have one stage. But likely you won't, so that means you probably have to have two stages. Another thing you can do is reduce the number of degrees of freedom that you have. Okay, what that means, in other words, is you can change W over L's, you can change currents, you can have every transistor biased in a different way. Yeah, but it's just hard to keep track of everything that way, and you're doing lots of little tedious calculations. Choose like a VD-SAT, let's say 1/10 of a volt or something like that, a pretty typical value, and sort of just use that. And you can use the current, set the currents later on in W over L in such a way that you get that size VD-SAT. Once you have that VD-SAT, and you can sort of use that as a design parameter. You can calculate GEM from it. You can check to see if you're in saturation. So it's kind of, that's an easy number to work with, and it makes it easier for you to do your hand calculations. Someone mentioned, do we start with hand calculations? Where does the SPICE kind of fit into this picture? If you go to SPICE too quickly, you're just not going to know what's going on. SPICE doesn't tell you how the circuits work. I mean, it'll give you what's gone wrong. It won't tell you how to make it better, right? So what you need to do is basically, if you have a nice easy value of VD-SAT to work with and so on, you can easily do some hand calculations to figure out if this circuit should likely work. Okay, then you go to SPICE to check yourself. Use SPICE as a check. Don't use SPICE as a as in the inner loop of your design process. If you do that, you're going to find that, like I've told you before, it's nice when it's really late at night and you just don't want to think anymore, and you just hope, I'll just try this and maybe the answer will just fall out and I'll be home free. I mean, yeah, it may work, but probably not. Right? And especially when it gets close to the wire, you might want to do that. But let me tell you, if you get the hand calculation fairly straight, and it doesn't have to be extremely accurate. I mean, that's why we talk about this percentage, this 10% thing. I mean, that's fine. That's more than accurate enough for this stage of hand calculations for figure out where your design, is it close to the right answer, and then you can check with SPICE to see if it's not. What was the final thing I want to say? Optimization. You have a figure of merit to work with, this power times area figure of merit. Don't start with that. Be reasonable about things. What that means is area is an issue, means current is an issue, right? So what that means is that you don't want to do something that just has a gigantic size transistor. What's a gigantic size transistor? Size of 1,000 would be big. Okay. It's not that you can't do that. You can certainly do set transistors of size 10,000 on a chip. That's not a big problem. It's not. You might want to do that sometime if you have to drive lots of current and you have some reason. But it's going to take area, and it's not going to do very good in this figure of merit this time, and you don't seem to have any specification that would require that. Right? So likely you don't need a transistor that big, right? And so don't do it. And keep the power levels down. I mean, if you fix VD-SAT as your number, how do you make VD-SAT? What's the two variables in VD-SAT? Well, it's current and W over L, right? And so you can use that later on to sort of figure out what W over L and current you have to optimize that figure of merit. Anything else? That's all I can think of. Any questions about the project or approach to it, or start simple, keep it simple. You don't get. Oh yeah. I guess the other thing is, go for the specifications early on. Okay, I mean, try to meet all those specifications. Okay, don't leave some of them off the end. If you don't have a circuit that works until you meet all the specifications. So don't worry about this figure of merit thing until after you've met the specifications. Right? Specifications it's kind of. I mean, if you don't meet all the specifications, that's a non-working circuit, right? So I mean, it doesn't matter if you make it the smallest circuit in the world. It doesn't meet all the specifications. It's just that the figure of merit means nothing, right? Okay, so I think that's important. So go for the specification and try them all. Make sure you do all of them. Yeah, the last specification was this output swing. You have to have the small signal gain valid over a fairly large range, and it said at 1 hertz. What that's all about is the TA a couple of semesters ago did a pretty nice circuit. It's fairly clever, fairly tricky actually. It kind of has a feedback inside of it that for setting the DC bias point kind of automatically. Okay, and you'll do it by you can run a curve, right? You'll figure out the bias, the center of swing, and so on. But what he did is sort of had this little feedback circuit. And that's what the 1 hertz thing's all about. I mean, it's a low frequency DC feedback that he allows it to set the DC bias. I've asked the TAs to tell you about how that thing works. But it's a pretty clever test bench. Okay, maybe a little too clever. Okay, and in terms of understanding it, but what the 1 hertz all about is it just means it comes from that test bench, but really what we're talking about is small signal gain when the output's at 0.3 volts, small signal gain when the output's at minus 0.3 volts, and you can use the .tf function to do that if you've set the DC bias points already, the input voltage already. So, okay, any question about the project? This is the core of the course, right? I mean, this is what this course is all about, these projects, right? And I made this one. The idea of this one is it doesn't count a lot of points, and it's and it's relatively straightforward this time to get yourself so you understand how this test bench stuff works. Get yourself an approach for doing the design approach. So ask questions about that. I mean, this is really to get you going, okay? Because after the projects we'll have after the midterm will be much more challenging, so to speak. Right. Much more fun. Right. Okay. Right. Okay. Any other questions about that one? Yeah. Okay. Start them right away. That's if I can just say something. Get going on those projects. Do not put them off. If you put it off, you're just going to find yourself in a very painful next Tuesday night. Okay. David said he got up to slide 26. Are there any questions about the current source material that he went over? Okay. I'm more than happy to redo anything that he did or anything else. Okay. So let's maybe start with this Widlar source. So maybe what I'll do is I'll go back later on and review some of the stuff if we have more time at the end of this lecture. The problem is, as you will see, area in if you want to do, let's say we have a 1.2 volt supply, and let's say it's a circuit that looks like, so let's say it's sort of a simple current source, okay? And okay, so what's the size of this resistor if we want to have a relatively low current? Like let's say it's 1 microamp. 1 microamp is actually quite low current, but let's say that you can definitely work circuits with 1 microamp. What would be the current if you had? What would the size of the resistor have to be? Well, this is 1.2 volts, and this is VT plus VD sat. So let's say VT is 0.3 volts and VD sat is at 1 microamp. Won't be a tenth of a volt, but let's say it's quite small, 0.05 volts or something like that. So it's 0.35 volts for VT plus VD sat. So that means this point's at 0.35 volts. Let's say our supply, instead of 1.2, the upper ends, it's 1.35 volts. Just to choose a random number, okay? That means we have 1 volt across this resistor, and if we want to get 1 microamp, that means this resistor would have to be 1 megohm. 1 megohm is a lot of area. It takes. Have we shown you how to do size resistors yet? how are you going to do the resistor size for your project? If you need resistors, because you have that area times power as your figure of merit, right? Is that true? Let me look at the specs. I didn't think about that. You have it there? Area calculation. Here it is. Calculate the area W over L for the resistors, minimum W at 0.5. Sheet resistance is 250 ohms per square. Let me explain how that works. Okay, thanks. All right. So the numbers you're given on to size resistors is the minimum. So how do you make a resistor? The way you make resistors is a bunch of different ways, but basically we're talking about thin sheets. You know, a semiconductor process, silicon process, is thin films. It's not a bulk thing, it's films. So you put down different layers, okay? Well, the layer, what you can use is for the gate of a transistor, okay, is made out of polysilicon, okay? Well, you can use that same material. Polysilicon is just polycrystalline silicon. And you can use that same material that's a gate of a transistor to make a resistor, okay? You can use other things as well. You can use diffusions and things like that. But let's say we take polysilicon or something like that. It could be some other film, and we'll use that to make our resistor. Okay, so it's just a strip of material sitting on top of the silicon. Okay, so this is the top view, right? If I had a side view, this is side view. You know, there's a little layer that we're talking about here, from here to here. In the top view, it looks like this. Okay, now it has a width and a length, kind of like a transistor. Okay. Now the question is, what is the resistance? Let's say I have some aluminum contact on this end and aluminum contact on this end, then I go up to my metallization, or it's copper, or whatever it is, right? So it's this period, is the center region, which is the resistor between these two metal contacts. Okay? Now, what is the resistance from here to here if I have a sheet resistivity, and the sheet resistivity that we're given here is 250 ohms per square. So what this sheet resistivity is all about, what that means is that for every square, and a square is defined as, if I had just a piece of material that is length L and width W, and W equals L, I call that a square. And if the resistance across that square from this side to that side would be 250 ohms if it's a polysilicon resistance of 250 ohms per square. Okay? I probably can try to get the formula we're working with here is, it's kind of like, it's a bulk conductivity. So this is ohms. Sigma is equal ohms per cubic centimeter. Okay, so that's the bulk resistivity. But like I say, it's a film thing we're talking about. So there's a fixed film thickness. So let's call that T. Resistance goes up as T goes down. Okay, so that's right. Resistance goes up as the resistive length gets longer. Okay, so as it makes it longer, the resistance gets higher. And resistance goes down as the resistive length gets wider. Okay? So the resistance is equal to L over W times 1 over sigma T. Okay? Well, W, if I take L over W, look at that number. If I break this thing up into a bunch of squares, right, how would I figure out how many squares I have here? I take L and divide it by W, and that tells me how many of these squares I have. So that's kind of why we call this ohms per square, but it's really just this formula right here. So this value right here is this R per square number, right? It's 1 over the conductivity times the thickness, okay, times L over W. Well, L over W is the number of squares, so this is equal to number of squares, okay, times R, ohms per square, okay. Okay, so That's how we calculate it. So you take your resistance and you divide. Now, what's the area of this resistor? And that's what goes into your formula for the calculation of area of your circuit. The area of this resistor is equal to W times L. Okay? So you say, okay, well, I know how to make this really small. I'll just make W really small. Yeah, that would help, okay, because you really worry about W over L over W for the number of squares. So the area, so you can set this ratio independent of what the absolute value of W and L is, right? Okay, of course there's some limit, okay, and you're given, I just saw in the notes, in the specification there, W has to be at least 0.5 microns. So you should use that for your value because you want that as small as you possibly can. And then you would want to make the length sufficiently long to be able to get a resistance you want, and you figure out what the value is. So let's take our 1 megohm resistor. How many squares will we need? Well, we divide by 1 megohm, divide by 250 ohms. Okay. So this is be equal to 1,000 kiloohms. This is 0.25 kiloohms. That means it's 4,000 kiloohms, or is this right? 4,000 kilo square. This is squares, right? This is number of squares, right? Is that right? 4,000. Oh, the K's are here. So it's 4,000 squares. So that's right. 4,000 squares. 4,000 squares of our minimum width is 0.5 microns. That means L has to be 2,000 microns, okay, or 2 millimeters. Okay, now, 2 millimeters means anything to you, but, you know, a not unreasonable sized chip is like 5 millimeters on a side, okay? So 2 millimeters means that we've got something that's sitting like this on this, you know. So this is really expensive, okay, right? I mean, so this is just one resistor, all right? And so resistors actually are very expensive. In fact, it's much, if you think about a transistor, what's a transistor size? Typically a W over L of, you know, let's say 100. That's a pretty big transistor. L, for that, it's going to be 0.13 micron for your technology. To get W over L of 100, that means W is going to be 13 microns. So you figure out the area of this, it's W times L, that's the area of the transistor. We're just saying the gate area is roughly the area of your transistor. Of course it's not, there's contacts and other things as well, but it's on the order of that, right? There's also contacts to the resistor as well. So it's 0.13 micron times 13 microns. So this is like about, you know, 1.6 square microns, okay, for this area of the gate of this transistor. What was the area of our thing here? It was 0.5 microns times 2 millimeters, right? So it's 1 square millimeter, or 1 million square microns, right? This is a big difference, okay, right? I mean, it's like we could have 1,000 transistors or more. I don't know what it would be, 600,000 transistors in this area of this one resistor. Clearly, you don't want big resistors, okay? So anything you can do to make resistors small is really pretty useful. Okay. What can you do to help get your bias? I mean, something very trivial you can do. What was the problem with my little circuit that I had, right? I was having to drop all sorts of voltage across this resistor, and I only dropped one VT plus a VD sat across one transistor. Well, what happens if I put two of these in series? Then I don't have. Then I have this point's 2 VT plus a VD sat, right? So I've dropped more of the voltage across the transistors, which are quite small, and less across the resistor. So the resistor can then be smaller. So you can put more transistors in series. You still can you don't have to cascode this. This can go, and this is your simple current source, right? Right? So here's your bias string. You can put some more transistors, diode connected transistors, to drop the DC voltage and make this resistor smaller. There's something else you can do. Okay, That's how resistors are sized, and that's just things you have to worry about. You can test, yes, you can. So yeah, you can even go all the way. Just have this whole thing, just a bias string of transistors. And problem there, and it's not into your specifications yet. Let me just say practically what the issue is. VT, the threshold value, has a fairly good variation to it, right? So let's say it varies by 50 millivolts or something like that. So it's sort of a 0.3 plus or minus 0.05 volts. And if you have a whole bunch of transistors in series, you can see one of the numbers here is going to be, let's say you had 4 transistors in series, it would be 4 times VT, so it would be 4 times this variation of the threshold. So you're getting a pretty big variation, but that's not a problem for you this time because we didn't give you any variation like that, so you could do that.
Questions?
Yes. Where are you?
Actually, why do we have to put resistor there? If it's so expensive, then why not we just take it out and then like put maybe like 2 or 3 diode-connected transistor?
Yeah.
Transistor.
Yeah, right. Now that's just saying. Yes, you can do that. And I'm just saying is there's variation. I mean, if we had 3 diode-connected transistors, okay, and we take off this one here. Okay. So what is, this is actually a little bit nastier, right? So I mean, the problem is you got 4 VTs plus VD sats, in series here, and you have to solve that equation. But the fact that or 3 of them here actually, 3 VTs, and there's variation on each one of these VTs, and so that'll just cause more variation of this current here because of this. So it's nice to have the resistor, which kind of doesn't get you so much dependence on this absolute value of this VT, because it has pretty large percentage variation. The resistors also have a pretty good percentage variation, though, too. So that's not like you're getting home free here. I mean, they have a variation of plus or minus 10% as well. Right? So, but just the VTs are particularly bad, right? Yeah. Plus, you have body effect. Well, that's not fun. You can tie off the transistors, right? But clearly, okay. So what I'm going to talk is other techniques besides to try to get small currents that help you, especially when you try to get really small currents, then you can become really sensitive to these, as you'll find out if you try putting this in. If you try to get a microamp, you're going to be really sensitive because you're really sizing these things in such a way that you'll be very sensitive to the values of VTs and WRLs. So here's another way to do it. Let's say you start off with a reference current that's fairly large that you can establish fairly accurately. Then we'll use that to derive a very small current. Okay, Widlar current source is one way to do that. Okay, Widlar current source is it's not so useful for MOS. This should be more clearly a bipolar device. There is parasitic bipolar devices on a CMOS processes. What that means is when you have depends on the process, but there's a bunch of different ways. Let's say this is a P-well process, okay, and this is a well inside your silicon substrate, okay, and in this P-well you have basically your in plus source drain diffusions, okay, and generally put a transistor across here, okay. But let's say we don't make this a regular MOS transistor, and what we do is I call this the base, I call this the collector, and I call this the emitter. And notice what I have here. I have a lateral transistor here with a collector, base, emitter. So this actually is a bipolar transistor. And there's other ones we can create as well. You can sort of see I have a N plus here, I have an N plus PN, so I could have a vertical transistor, which is an NPN as well. So you can make up bipolar transistors inside a CMOS process because you have both diffusions. The problem is they're not very good transistors. This spacing here is being set by photolithography. It's not being set by diffusions. In a bipolar process, what you have is you've got an N diffusion inside a P diffusion, and then you got N collector down here, right? So it's this distance right here. It's set by the two diffusions difference from each other that sets the width of the base. The narrower the base, the better the bipolar transistor. Here we're set not by diffusions, but we're set by this lithography. So this means, this means it's not nearly a good transistor. I mean, its frequency response characteristics aren't that good. The betas are quite small, but okay. But it has some advantages, some uses sometimes. Maybe not in the signal path, though sometimes this this is actually a diffusion inside a diffusion. So this is closer to the bipolar device, and so sometimes a vertical transistor can actually carry reasonably good current. Okay, so it's sometimes used for output stages because MOS just isn't good for doing lots of current, right? You have to make it huge. But here's a use for a bipolar transistor that it's not in the signal path. It's just to get a really low value of current. So let's assume that I have I'm using one of these parasitic bipolar transistors. And if you remember you should remember from 105, the collector current is equal to IS times e to the VBE over VT, right? So, this is VBE is the base emitter voltage, right? And that's true if this voltage, if there's just like a MOS device, right? If there's sufficient voltage across here to put it in active region, right? Okay. So let's assume this is an active region. Okay, this could be like a 1/10 volt or something like that usually. This is exponential dependence on the VBE to the collector current. What is our dependence in MOS? Square law, right? So in MOS, it's square law, right? We have IC is equal to a bunch of stuff, right, times VGS minus VT quantity squared. So we have the square law dependence. Here we have an exponential dependence. So in other words, what this circuit is doing, if you look at it, what we're doing here is here's VBE. You can sort of think of that as the VGS. Here's a VBE here. Now if we had a simple current source, we'd apply this base emitter voltage to this base emitter voltage here, and these two currents would be exactly the same. It's the same circuit that we use for MOS in bipolar. I mean, the first was in bipolar. We took that same circuit and used it in MOS, so we're going backwards now. So in other words, if you have this, the base emitter voltage is tied the same, that means for both of these transistors, the collector currents will be the same. Okay? Now what did we do here? We put a little resistor in series with this output transistor. That means the VBE of transistor 1 is now dropped across VBE of transistor 2 plus the current, plus the voltage drop across this, which is I0 times R. So the VBEs are not exactly the same. Basically what's going to happen is the second transistor, I collector 2, is going to be E of VBE1 minus I0 times R. And I0 is equal, and this is equal to I0, right? So I0 equals IS times e to the VBE minus I0 times R of VT. Well, this exponentially decreases the size of this current. So putting a little voltage drop here makes a big difference on how much current you get here. That's because of the exponential dependence. The square law dependence is not nearly so strong, so this doesn't work so well. Okay, you don't really get a big ratio like you do in bipolar. Okay, well, how do we analyze this? Questions? VBE1 equals VBE2 plus I0 times R. Get rid of that. VBE, if I solve backwards for VBE of my original formula here, right? VBE is equal to VT. VT is V thermal. I should make this, this VBE is equal to V thermal times natural log of IC over IS, right? IC over IS. So just solving for this. Let me rewrite this again. IC equals IS times e to the VBE over V thermal. There's no threshold voltage inside a bipolar device. Right? So I just solve for VBE here, and that's what this equation here is all about. So you end up with VBE equals V thermal times natural log of IC over IS. I substitute for the two VBEs, VBE1 and VBE2, okay? And IR is the reference current here. I0 is the output current. there's two different saturation currents. So if these transistors were different, I'd have different values of IS. I can, of course, make those the same type transistor, make them matching transistors. Then IS2 will equal IS1, and those will cancel out. So I end up with a formula that looks like this. I0 times R equals VT times natural log of IR over I0. And that's a transcendental. You're going to have to solve that iteratively to get the right value. Okay. Or, and for a design problem, it's easier, right? We can just take this formula right here and just solve for R, right? R is equal to V thermal over I0 times natural log of I reference over I0. So if you know what the reference current is, you know what output current you want, you can just calculate R. So the design equation for this is quite simple. The analysis equation is a little tougher. Okay? So you choose a value R, and you can easily, and this can easily ratio, let's say your basic. Typically what you do in a circuit is you have one reference current that you derive, and you do that as accurately as you can, and we'll talk about later today how to do this in a supply independent way. Notice all of these techniques we've talked about so far have supply. Let me just, here's our simple current source, right? So here's our output. What is the current through here? Well, it's going to be I ref, okay, is equal to VDD minus VT minus VD sat divided by R. Well, notice VDD is in there as a, linearly dependent on the value of VDD. Well, the supply voltage, typically you don't get that kind of control. People will give you, VDD will vary by 10% or more. I mean, the tighter you make that variation, the more expensive your design will be, because that means the power supplies then have to be designed to be more accurate. Okay, so so we can design circuits actually that are relatively independent of VDD. We'll show you how to do that. So it's a very different kind of circuit than this. Pretty tricky. Takes more transistors. Okay, so the problem there is more transistors, you only want to do that once. So typically what you'll do is you'll have one bias independent reference current source somewhere in your circuit on the chip. Then you'll take that and use it to bias up other parts of your circuit. Okay, and if you want a really small current, you would use that reference current and then use it to do a circuit like this to get a really small value of current if you needed that. So that's basically the idea. One reference current, and everything gets biased off that, and you can ratio off that quite simply, right? And we also talk an easy way to ratio off a bias reference current, right? Is you just simply go through a diode-connected transistor and change the W over L's, right? That's the easiest thing. I mean, if this is W over L equal to, let's call it reference, you make this 10 times W over L reference. If this is IR, well, this means this is going to be I0 times 10. So it's pretty easy to ratio currents this way. And if you made this 1/10 the W over L, then this will be 1/10 the times I0. Okay. What happens if you want to make this 1,000 times smaller than this? Then you got a problem. Then this transistor ratio is getting very large, and you got a big transistor now, just like you had a big resistor before. So that's why it's not so easy to even do this to get big, really small currents again from a reasonable size reference current. Okay, get that? Pretty handy thing to do here, this ratioing of currents by W over L ratio. Woodlight source. Here's another one. Similar deal. I mean, the bipolar works for these things. These do work for MOS, to a certain extent. And you can figure out, what's a better way to do it in terms of the area of your design and so on. Here's our reference current. We put a resistor over here, and basically the same thing is happening here. The goal we're trying to do is to basically reduce. We have a VBE1 here. This VBE1 corresponds to the reference current, right? Because this current's going right through that transistor, assuming the base current's fairly small. So VBE1 is given by this formula. But if we go around this circuit, we can sort of see what's happening here. We're going to have a voltage drop across here. So VBE2, if we see what VBE1 is equal to, VBE2 plus the voltage drop here, which is I reference times R, that's the voltage drop across here, right? Up to here, that's equal to VBE1. So VBE1 is equal to VBE2 plus I reference times R. So it's fairly similar to the Widlar source. Why is this maybe a little better? Anybody have any idea why this might be a little better source? Look at these two. Something dropped. Okay. Why is this probably better than this? Any takers? What? Raise your hand. Use the mic. Yeah. Okay. Voltage swing, he said. All right, thanks. So it's the voltage swing. What's going on here? This will get within this, in order to keep this device in active region, there's a minimum voltage you can have across this. Let's say it's like 1/10 of a volt, okay? Here, same deal. This, you have to keep at least 1/10 of a volt across this transistor, but now it has to be added to this I0 times R. So it's I0 times R plus, for bipolar, it's the equivalent to VD-SAT, in effect, right? Which we have to keep across this transistor. So this voltage will not be able to go as low on this collector as this one here. So this will have better swing. So current sources, there's a couple of figures of merit. One is how large the output resistance is. And this will have a little bit higher output resistance, right? Because of this this resistive degeneration. It's just like in MOS, you get the same effect, okay? Here we won't have that resistive degeneration, but here we have less output swing, right? Or have more output swing. So, here we go. Okay? All right, what I'm going to do now is take a break. Okay, so we'll come back. I'm actually going to do something else, not this next. I'm going to do the circuit. So let's take a 3-minute break, and then we'll come back. Is everybody's mic having trouble? Just yours? Could someone else try a mic? Just you.
Hello? Hello?
Okay, all right, okay. Try again.
Hello?
Okay. Yeah, right, it goes off, right? It dies, right? Someone's sabotaging you. Yeah. No. Yeah, if you're not, you don't have to. Okay. You don't have to have a partner if you don't want to.
Question
Okay.
is why do you get no current going through here? Because there's like
Base.
base current, right?
Yeah.
And it's like,
You do.
okay.
It's just small, right?
Why
Let's
is
say
it small?
beta's the ratio of this current, the collector current to the base current is like what? It's the beta, right? And so
Right, but this resistor makes this resistance a lot larger than. Right? I mean, I don't know. It's R pi here, right? Maybe R pi.
yeah, well, what's this current going to be through here, right? I mean, there's a collector current here, right? IC.
Right.
This is IC over beta flowing into here, right? So this is 1 plus 1 over beta coming in up here, right?
So it depends on beta.
It's a beta, yeah. With beta's greater than 10, right, then it's 10%, right? So it's not that big an error, right? But you're right, that's another error in there, right?
So when the cascade stages, right,
Mhm.
the R1 and the RNs come into play.
One loads down the other.
So, okay, so you have the stage and you have the R out from the and that's going to plug into the stage.
It's not parallel, it's series. let's say you take a voltage thing. So let's say this is voltage. So here's, depends on whether it's voltage or current. It could be parallel. So this is AV times V in, right? Here's our out, R in. And this is going to be a voltage divider, right, between R and...
And that gives you the V in that gives the next gate, the cascade.
In actual fact, what's almost easier, though, instead of doing that, is, you know, this... Let's say it's a stage like this. Just include this R in as part of that R out. Then you don't have to do this little voltage divider. Right.
So you get this, and then that's the independent voltage for the next stage.
Yeah, yeah. So just sort of, right, exactly. So this voltage right here is that voltage. Okay. 4, 3, 2, 1. Okay. Let's start again. Okay. Okay. Sit her down. Okay. We're going to do now, I'm going to skip to make sure you get this material as early as possible, to using current sources for loads. And then we'll go back and do the supply independent business, okay? So this is one of the very important uses of current sources. I've kind of been talking about this, you know, since quite a bit through the entire course, right, since we started. And it comes about because of the issue in a normal, if we try to use a resistor as a load, then what happens is there's a connection between the voltage across that. We like to make this resistor as large as we can. The problem is, if we have a certain amount of current flowing through here, that gives us a larger and larger voltage drop. So we're kind of limited by how big we can make this resistor. And if we're limited by how big we make this resistor, we're limited in our gain. Because remember, our gain is always GM times R0 in parallel with RD for this case, right? Minus that. So we'd like to make this really large, but we can't do that because of this voltage drop across it. Is there a way, but we need current in order to make GM big. So what we'd like to do is to have lots of current and a really large value resistor. How do you do that? You can't do it with a resistor. What you can do it with is a current source. So here's what we're going to do. So now we know finally how to do current sources. We'll put a current source here. And this is this model of a current source, which is a little bit tricky, right? Because this is the R of this current source is the small signal resistance of this current source. IL is the DC value of the current, right? So this model of a current source is a mix of a small signal and a large signal model. After all I've said all year about doing the problem separately, what do I do to you? I give you a model that has the two mixed up. Okay, right? So apologize. That's life. You're getting better and better, and I know you can handle this. Okay, so when you do the small signal problem, you basically put your finger over the DC current, because that's, you know, DC current is infinite resistance, right? And so you just open circuit it, right? Or set a value to 0. You want to look at it. And that's the small signal problem that you'll solve. When you're doing the DC analysis, you put your finger over the small signal RL value, right? And you just look at the DC current that's being provided here. Okay? So by putting a current source here, you see what we do now. We directly control the current through the driver transistor. That's really nice. Okay? Now all of a sudden we've got rid of that problem that we had earlier, right? Where we were very sensitive to this value of the voltage on the gate here. Okay? But we're going to set that current by the current source in the load. So now, like I said, when you do your project, what you can easily do, you set the VD sats, right? Well, now by setting the current here, you can easily determine what the VD sat of this is. You'll know what this ID is, and you can use the W over L to set whatever VD sat you want. Okay? So this is really nice. So current source loads are really good. What's the disadvantage of them? Why may you not want to do that? It's a speed issue. Sometimes you don't want a lot of gain, okay? And also, by putting another transistor here, like we're going to do with this current source, that adds more capacitance to that node. So actually the lowest, for a very high speed circuit where you actually want low gain, because remember I told you there's always a trade-off between speed and gain, okay? You actually make this resistive is a fine thing to do, right? Okay, and it actually probably has lower capacitance. But that's after the midterm, we're worried about that. Okay, right now, these guys are great. To put in a little current source here, we can get lots of gain really fast. We can control the current through our driver transistor, so we can set VDSATs. And here's the circuit. Okay, so let's just start with the good old simple current source, okay? Here's the reference leg on this side here, so this is IREF, okay? Here's the diode connected transistor. When you start figuring out what a circuit is, I don't know if David talked about this, but look for these diode connected things. Once you see that, you can begin to take the circuit apart. Once you see that, say, oh, a diode connection. Probably have got a current source around here somewhere, okay? You look a little closer, you say, yep, it's like a reference leg here. Yep, here's probably the output of that current source. Okay, so it's a way to break up the circuit when you look at a new circuit sometimes. Okay, so here's I out. Now, so this, or IL, I guess, to be consistent with this, okay? So here's the circuit that implements this. So in your project, you can't use an ideal source, but you've got one that's a pretty simple transistor equivalent, and that's this guy right here, okay? So what is the gain of this circuit? Who can tell me what the gain of this circuit is? Okay, you see if your mic whistles.
It's GMRO over 2.
Okay, GM. Okay, it's okay, good. Because let's say it's minus. No, over 2. Where's the 2 come from?
Because you have RO in parallel with RO.
Oh, okay.
So it's RO over 2.
Good. Okay, so RO is a little RO. Okay, so exactly. So there's RO looking up this way. Looking in here, you see a little R0, the small signal resistance of that transistor. Down here, you got an R0 as well. So looking into here, R out of this transistor is equal to RO in parallel with RO. Now, I should do RO2 and RO1. This is a PMOS transistor. This is an NMOS transistor. They will likely have different values of lambda. There'll be a lambda NMOS and a lambda PMOS. So even though they're the same current, the R0s could be different. Quite often are, okay? Quite typically, a lot of times in exams, I'll make them the same for you, but clear those two values. So it's really R02 in parallel with R01. And big G sub m for this circuit, short this. What do we see? Big G sub m is equal to minus little g sub m. So the gain of this circuit is just, the gain of this thing is equal to GM R out, which is equal to minus GM times R01 in parallel with R02. Okay? So output resistance, gain, that's about all there is for this circuit. Right? Biasing is really easy now. Now the question you're going to say is, okay, I'm telling you that I have established the current through this transistor. But how can I do that if I don't know the voltage on this gate? Because that also establishes the voltage on this current through this transistor, right? So this is a little bit tricky, okay? What I'm saying is, with this point of view, I'm saying that I'm establishing the current through this transistor and that the DC voltage on this gate is the right DC voltage so that this transistor is in saturation. Okay? That's kind of an assumption when I talk about this way, because this circuit here I talked about, these equations, only are true if this device is in saturation. And this is only in saturation if the right DC voltage is here. But that's kind of the way we think about this. We sort of set the currents, and then we go to work to make sure that we have the DC bias set so these transistors are in the right region of operation. And that'll be sort of what you'll have to do in your project. Right? Okay? Get that point of view? It's a little subtle, but it's critical. Okay. Now, with this, RL is equal to lambda P and lambda N, like I just said. So we end up with R02 in parallel to R01. GM, this is that little handy formula, is 2IDS over VD sat. Okay. We can plug in to this formula here, and we end up with this equation here. This now ends up, the gain ends up inversely proportional to the current. And that's like I've said before. Now this is really true, is that as you make the current smaller, because both of these resistances get larger and larger as you make the current smaller, this thing gets more and more gain as the current gets smaller. It's because of the very strong dependence on the output resistance of these transistors. They're inversely proportional to current, whereas GM only goes up as to the 1/2. So the resistance increases inversely with the current, and the GM drops as a square root, so you come off better and better off by the square root as you go to lower and lower currents. So this drives you to very, very low currents. Problem is, I told you, move into the subthreshold regime. Once you move into the subthreshold regime, then these equations are no longer valid. In fact, what happens then as the G sub m then goes as proportional to the current. So as soon as you get into the subthreshold regime, you no longer get this improvement with reducing. So as I'm reducing current, the gain goes up and up and up, and then finally sort of flattens out. And that happens when you get down to the subthreshold. And once you're in subthreshold, as I said, though it's not true, we won't worry about this till after the midterm, but this frequency response is getting really slow. So as we go to lower and lower currents, this is IL, this is gain. So as we go to lower and lower currents, we're not getting any more increasing gain once we're in subthreshold regime, but the circuit's slowing down more and more. Of course, it's losing less power too, but that's maybe good. But so generally we operate right in this corner right here. This is where we sort of get the maximum amount of gain, and just where we end up going into this subthreshold thing where we don't really win any more and more gain. Right? Typically what we're going for is lots of gain, okay? Lots of gain given the frequency response, because what we'll do when we put this thing into feedback, we will turn that gain into other things. We'll turn it into circuit performance that's actually better. So our op amps are all about, I mean, you think of an ideal op amp has infinite gain, right? Well, we won't have infinite gain, obviously, but we'll have lots of gain. We'll have gains of thousands or 10,000 or maybe a million. So constantly our game is to try to get lots of gain, and then we can use that through feedback to do other interesting things. So just kind of, that'll become more obvious later on. Okay, so this is the current source load for a simple, what happens if we do this? So what happens if I want to make the gain higher? What could I do? What happens if I did this? Okay, so what have I done here? I've added a cascode to the load. Okay? There's a cascode on the load now. Okay? So now, how much, if we had the same currents that we did before, let's say IL is the same as we had before, how much more, and all the transistors are the same, just like in this other one, how much more gain do I have with this circuit than I do with this circuit? Who can tell me? What's the factor? Improvement. V for victory, right? 2, right? It's 2 times bigger. Why is that? Looking down here, we see R02. Looking up, what do we see? We see a degenerated circuit here, right? So we have GM. Let's call this transistor 3. This is transistor, I don't know, this is 1, this is 2, 1, okay, right, 4, 3. Looking up into here, I have this thing is degenerated by this transistor right here. So I have GM3 times the output resistance of this, which is R01, times the output resistance of this stage. So looking up into here, I have GM3 times basically kind of R0 squared, right? Huge. So the cascading makes this extremely large compared to looking down, which is just simply R0. So even if the lambdas are quite different, this is going to be very large compared to this. So looking into here, my R out is simply R02. So you see a circuit like that, you don't need to do any calculations up here. Just forget it, right? Just you only have to worry about looking downwards, right? What's the disadvantage of this circuit? Swing, swing. How high can this go up before some transistor goes out of saturation? So what do we have to look for? We have to look, the question is, when does this transistor go into linear region? It goes into linear region when the VD sat across this transistor, when the VDS gets less than VD sat. Well, how do we figure that out? Well, this voltage right here, if these currents, everything's in saturation, we know that this voltage is at VT plus VD sat. We jump up to here, this is 2 times VT plus VD sat, right? We go down, or actually go up. These are going down, and this is going up. So this is actually, I should be a little more careful. This is VDD minus this, right? This is VDD minus this value, right? Now we go up. So this point right here is going to be VDD minus a VT minus a VD sat. So how high can this voltage go? It can get within 1 VD sat of this. So that means the maximum voltage, V max at the output before this device goes into linear region operation, and the R0 collapses, okay, we don't get this big value anymore, is at, how high can it go? Well, it can go up to VDD minus VT minus VD sat. That's the voltage here. And we have to drop another VD sat, so it's another minus VD sat. Okay, so it's VD. So this thing can, it's minus VT minus 2 VD sats from this supply. Now we could do this high swing business, right, to make this, so we get rid of this VT if we wanted to do that. Sure, you saw that. But that's a problem. So this hurts on the swing on the positive side. Swing on the negative side, how low can we go? We can get as low as 1 VD sat, right? We can get within, this can go as low as until this just gets down to a VD sat above ground. So this has a V min, if this is a ground, of VD sat. So the swing on this output is between VD sat and VDD minus VT minus 2 VD sat. Okay? Get that? When you're doing your project, it's going to be important because that's what you're going to have to do. The swing business, you look for your output and see how much swing you need to get, right? If it's just a single transistor, it's simply that, right? If you have cascode like this thing here, you got to worry about the fact that this voltage here is not ground. High swing, remember that's if you put a little supply, put a little circuit here that drops the voltage of VT, then you can get rid of this VT because you only need to have a VD sat across this transistor to keep it in saturation. Right now we have a VT plus a VD sat across this transistor. Too much. We're wasting voltage in a sense. We'd like to have this the minimum amount. We like to bias our transistor right at the edge of being in linear region because that's where we're not wasting voltage. The problem these days is this very slow supply voltages, right? And you can't afford to have any extra voltage on cross transistors above and beyond, which just keeps them in saturation. Because if you waste that voltage, it's going to come right out of what you need to have in your signal swing. So a really important issue. The new parameter, this was not a problem. I told you before. I mean, you look back in my notes 10 years ago when I taught this course, we didn't worry about this so much, right? But now it's really a big critical issue. Okay. Now, here is the circuit to end all circuits. All right. This is a really great one, okay? This one is typically used as the front end of any differential to single-ended stage, and it's got some really nice characteristics. It's our basic differential pair. But instead of having a current source load up here, which we could put two current source loads up here, what we put instead is a diode connected current source. So the loads here of this circuit are a current source. That's like a simple current source, right? So this current on this side, okay, is being mirrored over to this side. So IDS1, IDS4, this current coming out of this transistor right here is being set by this diode connection of this transistor, which is the current coming from M1. So M1 is kind of the reference current, right? This is kind of the reference current in our old, simple current source. Remember, before what we did is we drew it like this, right? So here is our reference current, and here is our output current. If you look here, the reference current is IDS1, and our output current is right over here, and it's going to be IDS4. So this sets IDS4 equal to IDS1. Now, is this a balanced circuit? Can we use half circuit analysis on this? No. This is not balanced anymore, right? We got a diode connection on this side. We have not a diode connection on this side, so this is not a balanced circuit. So we cannot use a diode connection. We use a half circuit analysis. Look at the output resistance on this side, and it's looking into a R0. Okay, looking down here, you see kind of an R0. It's actually more complicated than that, and we'll talk about that in a second. But notice looking into this side, if we wanted to take the output over here, what do we see? We see a diode-connected transistor here. So the output resistance on this side is really quite low. It's 1 over GM. Whereas this side, it's going to be R0 or something on that order. So that circuit is really unbalanced, right? In fact, it's so unbalanced, the signal on this side is not very useful at all because it has such a low output resistance. So this is a single-ended conversion. So that's what we call a double to single-ended conversion. Double means we come in with differential circuit, and we come out with only a single value. Now, why is this circuit so good about that? We could do that with our old diff pair that we had before, but remember we lost half of the current, and we had a gain drop of a factor of 2 if we only took the signal from one side. This mirroring here brings the current from this side, you can see what's happening, in over to the other side. See that? So this current here is mirrored over to here. So we get the benefits of the current in this transistor over on the output side. So part of the usefulness of this differential single-ended conversion, of this current source connection, is that we do not suffer the factor of 2 loss. In fact, if you short this like I show you right here, let's calculate big G sub m. Let's call this node voltage here Vs. We have the current on this side is VID over 2 minus Vs times Gm. That's equal to IDS1. IDS1 is equal to IDS4 through that current source connection. So that current's going down to here, and that's going right into our output. So I out, and let's figure out what IDS2 is. IDS2 is in this direction. It's minus VID over 2 times minus Vs, right, times G sub m, okay? So it's right here. Here's IDS2. Minus VID over 2 minus Vs times G sub m. I out is IDS4 minus IDS2, right? That's what I out is going to be. Yeah.
Sorry, but if you shorted the ground, wouldn't it just go straight to the... Oh, yeah, you shorted the V out, right?
Short V out.
So wouldn't all the current IDS4 just go into there because it's a resistor?
Go right into I out.
Yeah.
Yep. Right. I out equals IDS4
Oh, okay.
minus IDS2 because that comes the other direction, right? Okay. Exactly what you said, right? So let me plug in my formula for IDS4, which is actually the current over here. Plug in my formula for IDS2, which is this current right coming down here. Look at the VS's cancel. I end up with I out equals GM times VID, so big G sub M equals little g sub M. So we don't lose the factor of 2 in current. Okay? Little factor of 2. That's nice. Okay. There's some other nice things about this too besides that. Okay, everybody get that? So big G sub M for this circuit is little g sub M. If we take the output on this side here is, there's no current summing. We'd lose the current from this side. It's got a low output resistance, so we don't use the output from this side of this circuit, except for midterms. Great midterm problem. I try to. They're all the same, right? So we assume these transistors are the same here, right? So that's why I didn't put a value there. And actually, if you're a little more careful, we're talking about this GM and this GM here. So it's just these two GMs we're talking about. Okay? Any other questions? Here's trickiness. R out. So let's do R out for this guy. Looking into here, we'll do our old test voltage and figure out what the test current is. Okay? We drive into here, and what is a little bit, we can't use our half circuit because it's not a balanced circuit. Looking upwards, there's no weirdness. Looking up this way, what do we see? Basically, we see R04, right, to ground. There's nothing strange going on. Even that's not true. Okay, here, let me explain what's going on here. You should watch that. Let's drive this voltage here, and what's going to happen? If looking into this node lead here, what output resistance do we see looking down this way? R02. What is R02 equal to? It sees M2, but what is in the source of M2? M1. So looking downwards from here, which I've shown here, we're looking up into the source of M1. Well, what is that? That's 1 over GM times 1 plus chi. If the drain resistance of M1 is fairly low, right? Remember the old formula? It's R0 plus RD over 1 plus GM R0. So if RD is small compared to R0, then this thing becomes equal to approximately 1 over GM. Or 1 over GM times 1 plus chi if we keep that in the equation. Okay? So looking up, this is small. So that means looking up into here, we basically see 1 over GM. Okay? Let me forget the chi. Okay? So, all right, so looking into here, that's 1 over GM. Then what do we see looking down to here? I guess we leave the chi in because it cancels out, I guess. Looking down here, this is source degeneration of M2. So we plug into our old formula, R02 times 1 plus chi times GM times RS2. Well, RS2 we just calculated is equal to 1 over GM times 1 plus chi. So I'll put the chi back in, okay? So I put in 1 over GM times 1 plus chi into here, and what happens? This cancels, right? All right, sneeze. Oh, okay. Let me replace this by 1 over GM times 1 plus chi. The GM's cancel and the 1 plus chi's cancel. So this ends up equal to 1. So R02 looking down here is simply 2 times RO2, which is the output resistance of this transistor. Okay? So looking down this way, that we see that. Now, here's the really weird thing, or tricky thing. If we know what R02 is, it's this 2 times R02, and we know what VT is, how much current is flowing through this due to VT? The current right here, let's call it IS. IS, which is the same as the current here, is equal to VT over 2R02. See that? I mean, looking into here, that's just like an equivalent resistor, right? So it's R02. If I have VT right here, I know the current here is IS S, let's call it. I down, let's call it I down. I down, this is I down, and this is I down, this is I down, okay, is equal to V test divided by R02, and R02 we said was equal to 2 little r02, okay? Too many 2's. Okay, so that current's, watch it now, so this current's coming down here, it's going through this transistor, comes across here, where's it going to go? It's going to go up, the only place it can go, right? Now this seems weird, right? We were going upwards. How can we go upwards? I thought the current was going down. Gotta remember, this is small signal now, okay? These are, and this is actually grounded up here, right? So we're trying to get to this ground. We have a voltage here, and it's trying to get to this ground here. This is floating down here, right? This is kind of open circuit because we had a current source down here, right? This is DC current, so we open, for small signal, we open circuit that. Okay, so this is current's going up here. Now what happens to that current? So let's call this I down. I down then is mirrored over to here. So this current, which started here, going through here, up here, goes there, and then gets mirrored over here, and it's going upwards through M4. So remember, M4 is composed of two things. It has a dependent current source. And if you look at M4, it's small signal model, right? There's a dependent current source, GM times, VGS, and then there's an R0. This is transistor 4, right? And there's R04. So this transistor here has a current source and an R04. Well, this current source, I'm telling you, has a current in it of size VT over 2R02, which is equal to I down. That's the current source. How much current's going through R04? Who can tell me that? VT over R04. This is VT right here. The current going through the output resistance of this transistor is going to be VT over R04. Okay, so now let's sum up all the currents, I test. So I test is equal to a current going down, I down, right? A current going up, or another current, well, I'm sorry. So this current, I down is going up, so this current's going up. So there's another I down that's going up through this dependent current source, up through this transistor. So it's another I down. So we get I down twice. It goes down here, but then it gets mirrored and it shows up again, so we have to supply it again. Then there's plus this V test over R04, which is coming from this output resistance of this transistor right here. Well, what's I down equal to? I test equals 2I down plus V test over R04. 2I down, we said, I down's right here. It's 2 times V test over 2R02 plus V test over R04. This is equal to, these 2's cancel, I get V test over R02 plus V test over R04. Well, what's this? I need to calculate the ratio of V test over I test. So solve for this. This basically is the parallel resistor problem. So this is just comes out to be equal to R02 in parallel with R04. This is equal to R out. So R out of this circuit is basically equal to the R02 in parallel with R. It's this in parallel with this. You might say, well, that's kind of obvious. It looks like I'm looking here at the drain of this, it's R02. Looking at the drain of this, it's R04. That's the way to remember it. It's not how he got there, right? He got there because of all this other stuff going on. But the answer is simple. The answer, you look at this and say, well, it's just this output resistance of this in parallel with output resistance of that. Okay? Next time I'll do the common mode gain of this circuit. We don't have enough time right now. But this is a very good circuit to use for your project. Yes. Yeah, yeah, yeah. Right.